Hi, I'm Dominik Moritz, and I'm excited to tell you about our study on biased average estimation in line graphs. This work is a collaboration between Padilla, Nguyen, Steve Franconeri, and me. Leis and I contributed equally to this work. I also want to highlight that all of us work at different universities. After illustrating the motivation for investigating this bias, I'll go over the experiments and the results. Starting with the bias. William Playfair invented line graphs in 1786. Line graphs show a continuous variable's change over another continuous variable, typically time, as the changing position of a line mark. Line graphs have since become one of the most common data visualization types. Designers use line graphs to visualize stocks, sensor data, machine learning metrics, and human vitals, among others. The popularity of line graphs may be because the visual encoding of time series as the position of a line is considered effective, relative to other visual encoding channels, such as hue. We generally assume that visualizations, especially of effective visual encoding channels such as position, are perceived not perfectly, but at least without bias. Yet they are not. For example, prior work demonstrates that the background color can bias the perception of the color of a mark. And continuous rainbow color maps are perceived as discrete categories. There may be unexplored biases in line charts as well. When drawing a line, the length of a line drawn varies not only with the duration of the visualized time series, but also with the variability of the values. For example, take two time series of regularly sampled values over the same duration. The first value may not change much, while the second value has more changes. Both time series have the same number of values, so the same duration, but the visualization as a line graph shows that the second line has a longer overall length. Steeper line segments are longer than other line segments of the same length along x. The arc length of a line affects how much visual weight a line has, and so in other words, how much ink is needed to draw it, and how much this draws the viewer's attention. This increased attention or increased salience may bias the estimates of averages of lines towards areas of higher variability. To illustrate the bias, here's a line chart with low variability at the bottom and high variability at the top. In this line graph, you might estimate that the average value is at the red line here. However, the true average is lower at this gray line. And we want to investigate these three research questions around this bias. The first question is whether there is a systematic bias towards areas of higher variability in line graphs, as we have seen in this example. Second, since this bias may be caused by increased salience of steep lines, can we reduce the bias by using an encoding that doesn't make steep lines more salient, such as a dot encoding? And third, if the bias is due to increased salience, do we see it if we plot the points along the line, and can we use that to model the bias? To investigate these questions, we designed and ran two pre-registered experiments. The first one was to determine if there was a previously undocumented bias in the perceptual line graph estimation, and the second one to confirm the first experiment and also to determine if we could influence the degree of variability overweighting by changing the mark type. Here's how we set up the experiments and the stimuli. In the experiments, participants can move the grabber in our experimental interface up and down to where they estimate the line's average to be. To generate the stimuli, we start with a base series generated from geometric Brownian motion. This is a stochastic process that can be used to generate realistically looking data, for instance for stocks. And we also apply some smoothing. Then, we add linearly scaled random noise. The noise is higher for larger y values and smaller for lower y values. The noise is added to the points to move them. Finally, we scale the points since we added the noise. More details on the scaling are in the paper. There are some subtleties that need to be carefully considered here. The stimulus generation can be parameterized by the random seed for the Brownian motion and noise, and the variability levels. We also mirrored series to counterbalance potential bias towards higher or lower Y values. In experiment 1, 140 participants saw each 48 trials across a 2x2 within subject design. For 12 different seeds, we varied the variability from 0 to 0.15 and 0.4. And we used the unmirrored, which we call variability upper, and mirrored variability lower graphs. In experiment 2, 420 participants saw 48 trials across a 2x2x3 mixed design. For 12 different seeds, they saw a graph without variability and one with variability going from 0 to 0.4, mirrored and unmirrored graphs across 3 different mark types. In the first, we encode the data as line, then as point, and lastly as points, with points sampled along the arc of the line. Note that the average of the points in the last mark is not the true average of the points in the series. In the paper, we describe 5 hypotheses that we investigated. At a high level, the first experiment checks whether the bias exists, and the second one checks how it is affected by the mark type. We pre-registered the experiments and made all materials available online. Let's look at what we found. Starting with experiment 1, we looked at the distribution of the estimation errors across the 2 variability levels. The estimation error is the difference between the true and the estimated average. We found that the errors were higher, or further away from 0, with greater variability. The black bars within the density plots show 95% CIs with a mean dot. And we see the same across the mirrored and not mirrored condition. These results confirmed our first 3 hypotheses. For experiment 2, we looked at the normalized error across 2 variability levels and different mark conditions. The normalized error merges the error for the mirrored and not mirrored conditions. When we encoded the data as points instead of lines, the estimation error went down significantly compared to the line graphs. This is promising as it gives designers a way to graph the same data without biasing average estimations, if that is something important for them. Experiment 2 also confirmed that the bias is higher for charts with higher variability, so hypotheses 4 and 5 are confirmed. In the paper, we describe these experiments in detail, and also describe additional analyses. For example, we asked participants for their strategies and found that using the correct strategy reduced the estimation error. We also created a model to predict the estimation error for arbitrary line graphs based on just the true average and the average of the points drawn along the arc. In summary, we experimentally found that average estimates are biased towards errors of higher salience, caused by increased variability in the visualized data. Since the bias can affect the conclusions drawn from data, visualization designers must be aware of it. This bias is practically relevant. The variability in a line graph may be due to irrelevant factors such as inconsistencies in the data collection or varying sensor noise. We can also quantify this bias to make designers aware of it in tools, and we showed that encoding the data as points can mitigate the majority of the bias. Future work should investigate the causes of this bias further and how we design tools around it.